Swayam Prabha. Digital India. Educated India.
What I'd like to start talking about is Boolean Fourier analysis. Okay, so in keeping with the theme that I was developing, so now we'll formally define the Fourier transform. Okay, and we'll see how it played a role in the algorithms that we already saw. So that's what we should do next. So let's look at this. Can anyone remind the class what I said about this Fourier analysis? So remember, we did talk a little bit about how you can change the basis from the standard basis to the Fourier basis, and this can help you. So what was the idea there? Yeah, so you're saying that you apply a Hadamard and then measure. That is correct. That is how you implement it. But why are we doing that? It is because when we change the basis to the Fourier basis, we may get some patterns about the data which were not evident in the original basis, right. So that is the whole point of doing this. So let's remember that. So let's define the Fourier transform. So first we will define it over Z to N. Okay, so remember that the Fourier transform is, maybe I will write it. So remember that Fourier transform is essentially a change of basis. Okay. Okay, so first we will define some functions here. So consider a set of functions. So again we will set up a little bit of notation first. Yeah, so consider a set of functions. So this is a function which is 1 if x is equal to y and 0 everywhere else. Okay. So if I define this set of functions, then I claim that for any function, for any general function, this set of functions serves as a basis. And this is actually quite easy to see, because you could sort of, for each point, right, you can multiply this with the value of the function at that point and then just sum over all of these. So then in the end you will just get the truth table of the function. Okay, so we can write this. So let's see what notation we want here. So let g be a function from 0 1 to the n to c. Then I can write g of x as summation over all points y, gy delta yx. Everyone see why this is true, right? So this is really trivial, right? This what we've written. It's just saying that fine, if I want g of x, I will look at delta y of x, which is only going to be 1 when y is equal to x, and I will multiply with g of y, right. So this is just a very simple way of writing it. This is called the standard representation. Okay, let me write that with a different color. So, this representation is called the standard representation. Okay, so note that each function delta y, if I think of it as a vector, how many entries will it have? No, it will have one non-zero entry, 2 to the power n, right. So, you can think of the delta y, the basis vectors, as being vectors of length 2 to the n, where each one of them has a single one in a given position, right. So, it's like a long unit vector, right. By the way, you know, let's interchangeably start, as soon as I said this, I see that I will be abusing this notation. So, okay, in some places we will you know, use capital N to represent 2 to the n. Okay, so when we use RSA, when we talk about RSA, then you know, capital N also represents P times Q. So, outside that context we will use this. I hope that I will always define it, but in case I use it, you know, without defining it, then it's going to stand for 2 to the n, alright. Okay, so this is called the standard representation, and of course we already said that, you know, we can always represent any vector, any function using this basis, right. So, G can be written as basically, you know, G 0 to the n, G 0 to the n minus 1 1 and so on up to G 1 to the n. Okay, and the length of this vector is 2 to the n, yeah. And as we already said, so delta y is a column vector with zeros everywhere except the yth position where we have a 1. Okay. Okay. So, yeah, so far so good. So, now let us move to, you know, what we're hoping to achieve, which is a change of basis, right. So, for that I have to first of all define the basis. So, we have already sort of seen this in action when we did our quantum algorithms. Now, let us just simply make it, let us just abstract out the idea and see it from that lens. Okay, so remember that we defined you know, sigma times x as the inner product of sigma and x mod 2. So, this is just I going from 1 to n sigma I xi, all of this is happening mod 2, yeah, and this can be written as XOR of xi, where I is such that sigma I is 1. Okay, so writing it in this way, you can see why we think of this as a parity. So, it is the parity of x restricted to the positions where sigma is 1, correct? And now what we are going to do is, you know, we are basically going to take this idea, and instead of you know, using space 0 and 1, we will just move it to minus 1 comma 1, it will just be more useful for us. So, how should we do that? Well, instead of considering sigma x directly, sigma times x directly, by the way, remember when I say sigma times x, these are both vectors, okay. So, it should be clear what I mean by sigma times x, it's this, the inner product mod 2. So, now instead of just inner product mod 2, what I'll simply raise it to the exponent of -1. So, if I have -1 to the sigma x, then what happens when it is 0, the whole thing becomes 1, and when it is 1, the whole thing becomes -1. So, that's all. So, this is just a different, it's the same idea, but just the plus minus version of it. So, consider the plus minus version. Okay, so, -1 to the sigma x, this is 1 if sigma times x is 0 and this is 0, no sorry, it is -1 if sigma times x is 1. Okay. And this I am going to denote by chi sigma of x. Okay, and this is called the Fourier characteristic. Okay. By the way, a quick note here, which you will see comes in handy again and again. What is chi 0 of x? For any x, it is just 1, just by definition, very easily. Okay, good. So, everybody understood the definition of the function, right. So, now obviously what we want to do is develop a basis using this description. So, let us let me define a bunch of vectors, and we will have to prove that it is indeed a basis, right. So, let us define the Fourier basis as chi sigma, where sigma is in 0, 1 to the n. So, let us represent chi sigma as a vector here. So, similarly to before, so chi sigma 0 to the n, chi sigma 0 to the n minus 1 1 up to chi sigma 1 to the n, right. And once again note that this is of length 2 to the n. So, okay, so what did we do? We just defined a set of vectors, right. So, previously also we had done that. There we were using these delta y's, now we are using chi sigma. I mean it is a different set of vectors. I need to prove to you that this is indeed a basis. Okay. So, if I prove that this is a basis, then what can I say? Well, then I can say that any function can equivalently be written using this basis, and the coefficients that we will get there, the Fourier coefficients, we will have to figure out how to compute them. But then we will see that essentially the Hadamard transform, what it was doing was it was just changing the function representation to the Fourier basis. Okay, we'll come back to that. So, for now what I need to do is actually prove to you that this is a basis. So, what do I need to prove here? So, first of all there should be 2 to the n of them, right, because the space is of size 2 to the n. So, at least you need to have that many vectors. This is already true just by our definition of the vectors. The more important thing that we need to show is that these are orthogonal, right. So, now let us show that. So, what we will show is that summation x 0 1 to the n chi sigma x chi gamma x is 0 if sigma is not equal to gamma and is 2 to the n. otherwise. Now, why am I considering this inner product? Can anyone tell me? I am trying to show that the vectors are orthogonal. So, well, it is just the inner product of the two vectors, right. So, that is all. So, everyone agrees that this is enough, right. So, let's go ahead and show this. And one thing, like one nice way of thinking about this is actually to bring the 2 to the n over to the other side, okay, and then sort of think of sort of a randomly chosen x, a uniformly chosen x. So, let me write that. So, let us write this as 1 over 2 to the n summation x okay. So, we will just simply rewrite it in this way, that is easy. And now we'll sort of write this in terms of expectations, okay. So, this is E x, so x chosen uniformly from 0 1 to the n of chi sigma x chi gamma x, right. So, does everyone agree? So, it is just a different way of writing this. So, this just follows by expectation, just the definition of expectation, right. So, if x is chosen uniformly from 0 1 to the n, then any one of them has probability 1 over 2 to the n, and I am summing over all of them. So, looking at it in this way helps, it makes things cleaner. So, let us look at it like this. So, this is what we have set out to prove. Now, in order to prove this, right, so actually what's going to happen later is that maybe you already see it from the definition, but chi sigma x chi gamma x is basically nothing but chi of sigma XOR gamma x. So, we can look at that later maybe, but I claim that this is actually just this. Okay, so that's just it just follows from the definition. Okay, you can convince yourselves of this later, or yeah, we'll run into it again, so maybe we can talk about it more at that time. But the reason that we are seeing it this way is to convince you that it suffices for me to just understand what is E of x chi sigma chi of any one thing x. So, basically if I understand what is the expectation of x chi sigma x, then that's going to be enough for me to prove whatever I need to prove. Yes. Sorry? It's just expectation over x is what I meant to say. So, where x is chosen from 0 1 to the n. So, just to sort of clarify what is the random variable here. Okay. So, now let's consider Ex chi sigma x. Okay. So, what I was hoping to show you here in the last line is that the product of two of these chi's can equivalently be seen as a single chi for a different a different sigma or whatever. So, I do not know what to call it, like a different subscript. So, let's just look at what is the expectation for any fixed sigma, what is the expectation of uh, chi sigma x over x, right. So, this is just let's just write this down. Okay, so case 1, sigma is not equal to 0. So, if sigma is 0, of course, this is very easy. So, if sigma is not equal to 0, then I can write this as Ex minus 1 to the sigma x, right, which expanding this out, this is just going to be product of I such that sigma I is 1 minus 1 to the xi. Okay, now this is so far just sort of opening up the definition. Now, there is one important simplification I can do, which is from the fact that these xi's are all IID. Okay, so because I said that I am choosing the vector x uniformly, this is equivalent to saying that each bit of xi, every bit of x is chosen uniformly. So, this means that I can actually bring the product outside. Okay, so let us do that. So, E of xi minus 1 to the xi, right. So, now I need to only look at this. And now this is very easy to compute. So, this is half times minus 1 to the 1 plus half times minus 1 to the 0, right, and this is just 0. Does everyone agree? Okay. And case 2 is quite easy. So, case 2, if sigma is equal to 0, then it is very easy to see that Ex chi sigma x is simply equal to 1. So, it is just minus 1 to the 0, right. So, what did we get? So, we got that Ex for x uniform chi sigma x is 1 if sigma is equal to 0 and this is 0 otherwise. So, now consider our original problem, which was Ex chi sigma x chi gamma x. So, this is Ex so this is just this, right, just opening it up, and this just means it is Ex pi sigma I XOR gamma I equals 1 minus 1 to the xi. You can convince yourselves of this offline if you are not already convinced. So, this just means it is Ex of chi sigma XOR gamma x. Okay, so, this is going to be 1 if sigma XOR gamma is 0. else it will be 0. Okay. So, what does this mean? So, sigma XOR gamma is 0 when? If the two are equal, right. So, basically this is just showing what we wanted, right. So, we wanted to show that these vectors are orthogonal and this is showing that. So, yeah. So, whenever sigma is not equal to gamma, the inner product is 0.